Hi friends, in this video our topic is armature reaction. The main concept in synchronous motion is armature reaction. Without armature reaction we can't do parallel operation. Of course parallel operation is main concept, but parallel operation mainly depends on armature reaction. Without armature reaction, we can't do parallel operation. So listen carefully, very important. If you listen carefully, you can get easily, otherwise you get confused. Right? Right, sir. Listen here. So armature reaction. What is armature reaction? First of all, what is the definition of armature reaction? Armature reaction, nothing but the effect of armature flux on main field flux. What is that? Armature reaction, nothing but generally there is a main field flux and there is a armature flux. This armature flux will disturb the main field flux. This effect is called armature reaction. The effect of armature flux on main field flux is called armature reaction. This is very clear. So let's see, in generally, in our alternator, I told you already, for example, this is the main field flux and this is our EMF. EMF nothing but the EMF induced in the armature. For example, I am taking case 1 as a pure resistive load. What is that? Pure resistive load. Pure resistive load, bole to what is the power factor? Pure resistive load, nothing but the power factor is unity power factor. Unity power factor, pure resistive load. At this condition, in armature, what is the angle between armature voltage and current? The angle between voltage and the current is zero. The angle between voltage and current is zero. Here the armature current is in phase with EMF. When the armature current is in phase with EMF, then the armature flux also here, because the armature current produces armature flux. So let's see, actually the main field flux is in this direction and the armature flux is in this direction. Here my armature flux going to disturb the main field flux, of course. But is it in opposite direction? No, not in opposite direction. Is it in same direction? No, not in same direction. But it crossing the main field flux. It crossing the main field flux. Then tell me, what is the type of armature reaction? Is this the demagnetizing or magnetizing or cross magnetizing? Yeah, very good answer. Here the armature reaction is pure cross magnetization. Pure cross magnetization effect of armature reaction. Pure cross magnetization effect of armature reaction will take place at unity power factor or pure resistive load. Is it clear? See here, actually here my main field flux is like this. This is my main field flux. But my armature flux is after 90 degrees. So how it is after 90 degrees? Nothing but like this. This is my armature flux. See, this is crosses the main field flux, but it is not adding, not subtracting. That's why this is pure cross magnetization effect of armature reaction. Nothing but there is no change in flux. There is no increment in flux, no decrement in flux. The flux is constant. Hence the voltage also constant. Hence the load voltage also constant. There is no change in excitation. There is no change in voltage. That's why this is called normal excitation. Normal excitation. Normal excitation will take place at what load? At unity power factor load, at pure resistive load, at pure cross magnetization, you will get the normal excitation process. Very good, sir. This is case 1. Next to generally again, this is for example main field flux, and this is my armature EMF. Now case 2, pure inductive load. What is that? Pure inductive load. So tell me, pure inductive load, nothing but what is the power factor? Zero power factor lagging. Zero power factor lagging. Zero power factor lagging, nothing but what is the angle between current and voltage? Current and voltage displaced by 90 degrees. The voltage is here and my armature current is here. The angle between voltage and current is 90 degrees, cos 90 is 0, 0 power factor lagging, and here is my armature flux. So let's see here, this is the direction of main field flux and this is the direction of armature flux. Here my armature flux disturbing the main field flux, exactly disturbing. In which direction? Is it crossing? No. Is it in same direction? No. Is it in opposite direction? Yeah, exactly, it is in opposite direction. Here, see, actually, my main field flux is like this, but my armature flux is after 180 degrees. My armature flux is after 180 degrees, exactly opposite to each other. Then what happened? Here the resultant flux reduces. When the resultant flux reduces, then EMF reduces, then terminal voltage reduces. In order to maintain the constant terminal voltage, what we have to do? We have to increase the main field flux. When this main field flux increases, then the resultant flux increases, then our EMF also increases, then the terminal voltage maintains at constant. Nothing but here it increases the main field flux, nothing but what happened here? Here excitation increases, nothing but this is over excitation. In order to maintain the constant terminal voltage, the machine operates at over-excited condition. Over-excitation. This is over-excitation. And what is the armature reaction? The armature reaction is pure demagnetization effect of armature reaction. Pure demagnetization. Yes or no? This is pure demagnetization effect of armature reaction. This is pure cross magnetization effect. This is pure demagnetization effect. Now the case 3. You have to draw the case 3. Hold the video and derive for case 3. Same case 3. Do it first. Do it first. Hold the video and do it for case 3. That is pure capacitive load. What happened? Give me the answers first. Give me the answers first. Yeah. This is, for example, my main field flux. My main field flux. And this is, for example, EMF. Right? Yes or no? Now tell me, I am taking case 3. What is case 3? I am assuming pure capacitive load. If it is pure capacitive load, what is the power factor? Zero power factor leading. Zero power factor leading, nothing but what is the angle between voltage and current in the armature? The armature current is 90 degrees leading. 90 degrees leading to the EMF, as well as our armature flux also same. Then see here, this is my main field flux direction and this is my armature flux direction. Now tell me, here my armature flux is disturbing the main field flux, but in which direction? In opposite direction? No. In cross direction? No. In same direction? Yes, both are in same direction. Nothing but additive or subtractive. Additive, exactly additive. So pure demagnetizing or cross magnetizing? What is the armature reaction in case 3? Pure demagnetizing or pure cross magnetizing? Very good. Pure magnetizing. Very good answer. So what is that? Here, pure magnetization effect of armature reaction. Pure magnetization effect of armature reaction. But here, actually, when two fluxes are added, the resultant flux increases, EMF increases, and load voltage or terminal voltage increases, which is very dangerous. So, in order to maintain the constant terminal voltage, we have to reduce the main field flux. When main field flux reduces, the flux reduces, resultant flux, and EMF reduces, then the terminal voltage maintained at constant. We have to maintain terminal voltage constant. So in order to maintain constant terminal voltage, the excitation reduces, nothing but this is operating at under excitation condition. Here pure capacitive load, zero power factor leading, and here pure magnetization effect of armature reaction, and this is under excitation. Yeah, up to now we completed 3 cases. Now the special cases, case 4 and case 5. Pure resistive, pure inductive, pure capacitive completed. What is next load? Very good, resistive and inductive load. And the next load, resistive and capacitive, right? So let's see here for next load, resistive and inductive load, simply called as RL load. Fourth one, right? So the fourth case is RL load, resistive and inductive load. The resistive and inductive load, nothing but what is the power factor? Simply lagging power factor. Here phi is in between 0 to 90 degrees. We don't know how much it is. And see here, generally here the main field flux, and here our EMF equation, EMF, and here the angle between current and voltage is in between 0 to 90 degrees. For example, this is my armature current because of lagging load. Of course, my armature current also here. And see, this is my main field flux direction. And here, this is my armature flux direction. See, some part is crossing, some part is opposing. Then tell me, what is the effect of armature reaction here? Some cross magnetizing, some demagnetizing. That is technically called as partially cross magnetization and partially demagnetization effect of armature reaction. Partially cross magnetization and partially demagnetization effect of armature reaction is this RL load. And even though here demagnetizing, that's why flux decreases, then we have to increase the excitation in order to maintain the constant terminal voltage. So this is operating at over excitation condition only. Over excitation condition only. Right? This is for RL load. Can you draw for RC load? Do it, hold the video and do the answer for RC load. Come on, do it. Come on, do it for RC load. Next one, case 5th is the RC load. Do it, ma, do it fast, ma, do it. So the 5th load is the RC load. RC load, nothing but leading load. the angle, the power factor angle is in between 0 to 90 degrees. We don't know how much. If you say R and C, we can say phi is equal to tan inverse of XC by R. Like that we can find, but we don't know R and C values. So again here, for example, my main field flux, and here my EMF E, and the angle between current and voltage is lagging, not lagging, leading some angle phi. Again here, see, this is my main field flux direction, and this is my armature flux direction. My armature flux direction. Nothing but here some part is crossing, some part is adding. Now tell me, what is the effect of armature reaction is here? Very good, very good. Partially cross magnetization and partially magnetization effect of armature reaction is this. This is the over-excited or under-excited? Flux increases, that's why this is a under-excitation. Under-excitation. This is simply for RC load and RL load. This is very clear, a armature reaction. Are you okay? Yes or no? So let's see the overview of our armature reaction for alternator. Alternator armature reaction overview. Let's see here. Very easy to remember. Let's see here. This is my main field flux, and this is my EMF. This is actually vectors. If it is unity power factor, then armature current is here and armature flux is here, and this is a pure cross magnetization, and this is a normal excitation condition. If armature current and armature flux is here, nothing but pure inductive load, nothing but zero power factor lagging, so exactly opposite, that's why pure demagnetization effect of armature reaction, and this is operating at over excitation condition. If armature current and armature flux is here, that is pure capacitive load, nothing but zero power factor leading, and nothing but pure, both are in same direction, that's why pure magnetization. So this is under excited condition. If my armature current is here, that is RL load, nothing but lagging load, nothing but lagging power factor, nothing but lagging power factor, and the armature reaction is partially cross magnetization and partially demagnetization, and this is also over excitation. If the armature current is here, this is RC load, nothing but leading power factor. The armature reaction is partially cross magnetization and partially magnetization. This is under excitation. This is clearly what is armature reaction. Very simple in one diagram. A very important topic in synchronous machine. Within 1 minute you can cover. Right? So now tell me, pure resistive load. For pure resistive load, nothing but unity power factor. Nothing but cross magnetization. Nothing but normal excitation. Next, pure inductive load. Nothing but zero power factor lagging. Nothing but pure demagnetization, nothing but over excitation. Next, pure capacitive load, nothing but zero power factor leading, Nothing but exactly magnetization, nothing but under excitation. And next, RL load. RL load, nothing but lagging power factor. Partially cross magnetization, partially demagnetization. This is again over excitation. This is case 1, this is case 2, this is case 3, this is case 4, and case 5. You have to draw. You have to write case 5. I given you already case 5. Note down and draw this one and write this one. Very important. Are you okay? Getting or not? This is what the armature reaction. Okay, the concept is completed. I will ask you one question. Now tell me, in synchronous machine, armature reaction depends on. In synchronous machine, armature reaction depends on. Armature reaction depends on. Option A, type of load. Option A, type of load. Option B, magnitude of load. Magnitude of load. Option C, speed. And option D, I won't give you option D. Now tell me what is the correct answer. Tell me. In synchronous machine, the armature reaction depends on type of load, lagging load, leading load, unity power factor load. So it depends on type of load as well as magnitude of load. If load increases, the armature reaction also changes. So it also depends on magnitude of load, but it won't depends on speed. It won't depends on speed. So what is correct answer? A and B is the correct answer. The armature reaction depends on type of load and magnitude of load, but not on speed. Is it okay? Right? This is clear? Thank you.